Thanks for joining. Today we're going to be talking a little bit about RocksDB, which is a technology that came out of Facebook, and over the last, probably six months or so, as we've been optimizing LittleHorse for performance and for scale, I have come to know RocksDB a lot better and come to appreciate, how beautiful it is on the internals. So, I hope that at the end of today's talk, you'll have a better understanding of how it works, how to configure it in production, and how LSM tree-based storage engines work. This extends beyond just RocksDB itself. I think a lot of these concepts will be applicable to other systems like Cassandra, which are also based on LSM trees. This is highly relevant to Kafka Streams developers. I'll have a couple points which are only I'll probably spend about 4 or 5 minutes of today's half-hour talk specifically dedicated to some Kafka Streams only topics, such as the Kafka Streams state stored cache and how to access RocksDB configurations within a Kafka Streams application. Because Kafka Streams is one of my favorite technologies of all time, and I'd be remiss if I didn't spend some time on it. Actually, I forgot to do the obligatory "Can you guys hear me?" Question. If any of you can hear me, could you put a comment in LinkedIn, please? Oh, no comments. Hang on, let me check. Trying to figure out if the microphone's working. Okay, cool. Looks like the microphone's working. All right. In this case, I think it's time to start with the presentation. So I will share my screen. Share the screen. Okay. Whoa. 10 things I have to click to do this. All right. Here we are, finally. RocksDB write path. So this is basically how does RocksDB process writes, but in the process of learning how RocksDB processes writes, we're going to learn a lot about RocksDB. So we're going to start with what is RocksDB, the overall architecture, and then define a bunch of terms, including memtables, SSD files, the write buffer manager, with a shout out to SpeedyB, block cache, Bloom filter, and then talk about Kafka Streams configuration specifically, and then overall general recommendations for configuring RocksDB, either for in general, or if you care about limiting memory usage and avoiding out of memory errors. So what is RocksDB? It's a high performance embedded storage engine that came out of Facebook based on the LSM tree architecture. We'll define the LSM tree architecture over the course of the presentation. You'll just kind of understand what I mean by that. But what I meant by embedded storage engine is actually an important point, which means that it's an embedded storage engine, which means it's not a server where you issue requests to the server and over the network, and the database responds. So, for example, when I use Postgres as a database, I open a connection to Postgres and send queries to Postgres over the network and receive responses over the network. In contrast, RocksDB is an embedded storage engine, which means that it lives inside your application and has a C++ API with a Java JNI in the case of Kafka Streams. It's used by many cool technologies. A few of my favorites are Yugabyte, which is a distributed Postgres implementation, fantastic database, probably my favorite database of all time. Kafka Streams and Apache Flink and many other things, I think, including Rockset. And SpeedyB is really, really cool up-and-coming technology, which is a fork of Kafka Streams with several improvements and features on top of it. I'll talk about one of those features today. There's many. I don't feel like I can do most of those features justice, but I will start with one of them. So first of all, RocksDB architecture overview. Well, here is a Excalidraw of the RocksDB architecture. And as you can see, it's a layered architecture, much like Shrek. So how does it work? When you make a write into RocksDB, basically RocksDB has byte strings, arbitrary byte strings as keys, and arbitrary byte strings as values. So if I want to put some arbitrary key, it gets written into the memtable, the green memtable, which is the active memtable. And that's basically the most recently written data, active data that has been recently written. It's basically, you could think of it as an in-memory hash map. The actual implementation is slightly more complex, but it's basically just a hash map of key to value. So when I make a write, it goes into the mem table. What about reads? Well, as we go further down this picture, we get older and older data, which means the most recent data is in the active mem table. Then we have read-only mem tables, which are a little bit older and then older. And then L0 has a bunch of SST files, which are basically when the read-only mem tables get flushed to disk. And then beyond that, we have different levels with SST files that are increasingly old and old data. So naturally, when we're doing a read, we start with the most recent data and then move downwards. So if I'm looking for the key, 1, 2, 3, 4, I check this mem table, it's not there, check there, it's not there, check there, it's not there, check there, it's not there, and then go down the levels, and eventually I find it in L2, or maybe I don't find it at all. That's how reads work. And anyway, if you have any questions, just put a comment in the LinkedIn thing, and I should hopefully see it. Anyways, if I'm going too fast. So don't forget the write-ahead log. I didn't mention it in this architecture picture, but if you're paying attention, you'll note that the mem table is in memory. It's a hash map, and if I make a write to memory and then the database crashes, I lose that data. Well, the write-ahead log is just basically a way for RocksDB to enable recovery in the case of a crash. Basically, what it does is when you insert into the mem table, it also writes a key value pair to the write-ahead log on disk. And then when there's a crash recovery, RocksDB will reconstruct the mem tables from the write-ahead log. It's disabled in Kafka Streams because in Kafka Streams, the changelog topic is used as the write-ahead log, which is a Kafka topic in Kafka Streams. This is not a Kafka Streams presentation, so I won't go into too much detail about it. If you know Kafka Streams, you'll understand what I mean. So for mem tables, this is the first term that we're going to define. We already mentioned it earlier. But I wanted to talk about the process of a mem table going from the active mem table to a read-only mem table and then to the L0 SST files. And then when we get to compaction, which is the next slide, we'll talk about going from L0 to L1, and we can extrapolate that down to Ln. So when you make a write into RocksDB, you put it into this in-memory data structure called the active mem table. And eventually that mem table will get full based on the write buffer size, which is a configuration that you can pass into RocksDB. When it has, when it's bigger than that size, then the mem table becomes a read-only mem table, which is then a candidate for being flushed to an SST file. SST is, I think it's sorted string table. If there's any SpeedDB folks on this, presentation, please correct me. But anyways, mem table gets full, becomes a read-only mem table, eventually becomes flushed into L0 SST files. Now, note that there could be some overlap in L0. And that's not good because that means when you want to check L0 for the presence of a certain key, you need to check all the SST files potentially. In later SST file, in lower levels, the SST files don't overlap, which is great because that means you only need to check one SST file per level. Now, how do you go from a bazillion L0 SST files to having the nice, orderly, non-overlapping ones below? And how do you go from having duplicate data written in multiple levels, because you could have the same key written in the active mem table, then also in L0 somewhere, and then in L1, and also in L2. And the only one you care about is the most recent read in the active mem table, for example. That process is called compaction, wherein old data is merged and duplicate data is reorganized and duplicates are eliminated. Space amplification goes down. It's basically compaction is a well-known term, but basically combines it gets rid of older data and merges data on different levels so that you don't have duplicates. I think I should mention the term of write stalls. So RocksDB, sometimes if you have a lot of SST files and you maybe have a small write buffer size, these mem tables get full really, really quickly. You're doing a lot of writes. You have a lot of L0 files. That's not good. RocksDB might say, hey, slow down a bit. I can't handle all of these writes. And then it does this thing called a write stall, which means that the put operation will block for a while compaction is running. That can be disastrous in some applications. For example, Kafka Streams. I have seen it in some cases cause transaction timeouts in exactly once processing, which is really, really bad because that leads to, prior to Kafka Streams 3.7, that leads to a full state restoration. Really bad. You don't want write stalls. We'll talk about how to avoid that later. So the next thing I want to define is Bloom filters. We're kind of pivoting a little bit. I know I said we're talking about the write path, but Bloom filters are an optimization for reading. As I said before, you need to check different levels for the presence of a key. First you check the mem tables, then you check the L0 SST files, and then you check whichever SST file in L1 through N might have your data. Now, you can either load the SST file off of disk into memory and then check to see if the key is there, or you can make an educated guess as to whether the key is there. So a Bloom filter is an in-memory data structure that can basically tell you whether a key is in the SST file or not. And one important characteristic of the Bloom filter is that it can have false positives but never have false negatives, which means if this SST file right here contains the key Bob, then the Bloom filter will always say yes, the key is contained there. However, let's just say this SST file does not contain the key Bob. The Bloom filter might sometimes say that Bob is contained in there, in which case you end up actually going to disk and reading the data from though the data actually did exist. So Bloom filters can take up quite a bit of memory. We're going to talk about some things that you can do to reduce that memory, and also some things that we do at LittleHorse when we use RocksDB to reduce that memory. Next thing is block cache. The block cache is similar to the page cache in Linux, except there, it's basically a LRU cache over data read from disk. A couple differences from the Linux page cache is that if you have compression enabled on RocksDB, the data stored in block cache is uncompressed rather than compressed, which, because when you store it on the page cache, it's already compressed. So when you read from block cache versus reading from the page cache, RocksDB doesn't have to do any decompressing of the data. The next thing is we'll see something about how the block cache can be used to reduce the reduce the memory footprint of index and Bloom filter blocks, which are coming up later. But remember, Bloom filters are an in-memory data structure, generally in-memory data structure that can be used to tell you whether an SST file might contain a key, and index blocks are also in memory. We'll get to that again later. So now we're going to pivot a little bit to how you might configure RocksDB in production to avoid memory usage. Now, if you've used Kafka Streams or followed the Confluent community Kafka Stream Slack channel, it's full of people having, oh my goodness, I'm getting out of memory errors on my Kafka Streams application. And most of the time, that's because of poor RocksDB configurations. I love Kafka Streams and I love RocksDB. However, the default out of the box RocksDB configurations in Kafka Streams are just a ticking time bomb. So we're going to talk about the configurations that you need to set if you want to have a production-ready Kafka Streams application, or anything based on RocksDB. Actually, this is not just for Kafka Streams. So, what can use memory in RocksDB? Generally, there's three things. Obviously, if there's any real experts here, you're going to say that there's more, but these are the three biggest. So mem tables and write buffers. And if we go back to the architecture thing, that's these things, right? These things take up a lot of memory. The next is the block cache, which is what I talked about earlier, which is an LRU cache over data written and read from disk. So basically when you read, it gets put in the block cache, and reads they check the block cache before they check disk. And then the last thing is index and filter blocks, filters being Bloom filters. You have one index block per SST file, and you can cache the index and filter blocks, or you can partition them. Either of these mechanisms, we'll talk about both, are RocksDB specific features that allow you to reduce the memory footprint of the index and the Bloom filters. We're going to get to that when I show you the LittleHorse RocksDB configuration code. So next, we're going to talk about the write buffer manager, and then after that, we're going to talk about SpeeDB for a minute. So the write buffer manager, I think write buffer and mem table are roughly interchangeable terms in RocksDB and in SpeeDB as well. The write buffer manager determines when to flush one of the mem tables, and by flush a mem table, that's going back to here. It's this process of taking a mem table and turning it into an SST file on disk. That is flushing, not flushing the toilet. The write buffer manager has a couple of configurations. You can configure the maximum size of the write buffer manager, which says, hey, the total size of memory across all of the column families or RocksDB instances of all the mem tables in my application cannot exceed this size. You really should do that. I think out of the box, Kafka Streams does not do that, which means that you can have out of memory errors if you have a lot of open state stores in Kafka Streams or in any RocksDB application. And I want to note that in RocksDB, flushing is passive. Flushing is passive, which means that when you do a write to a mem table, or when you do a write to a column family, which is short, basically you think of a column family as a RocksDB instance. I don't want to go into that because I don't have too much experience with different column families since Kafka Streams only uses one column family per RocksDB instance. But when you do a write on a store, the store will ask the write buffer manager, should I flush any of my mem tables? And the write buffer manager will say yes or no. And two things I want to emphasize here, that the write buffer manager can be global, which means that you can have multiple RocksDB instances open on a server or on an application. Multiple RocksDB instances open on a VM or server or whatever, and they can all use the same write buffer manager. That is good practice. You should definitely do that. The next thing to note, though, is that the write buffer manager only does a flush when you do a write to the column family, or when you do a write to the database instance. So for example, if I have two RocksDB instances open and one of them has a bunch of mem tables that are using 90% of the overall space of the write buffer manager, I stop writing to that database, I'm only using the other RocksDB instance, and that would mean that the data in the first one, which is just sitting there, is never going to be flushed. It's just going to sit there because I'm not doing any writes to it. And there's a solution to that in SpeedDB. SpeedDB, remember, is a fork of RocksDB. I highly recommend you check it out if you're actually using RocksDB in production. So SpeedDB, the write buffer manager, is smarter and will flush proactively. So basically, it will flush data even if there aren't any writes going to that column family. This will have some applications in LittleHorse. We're doing some benchmarking of how it actually impacts LittleHorse, but it's a really, really cool feature. There's many other cool features like this in SpeedDB. Highly recommend you check it out. I won't try to do them all justice, though. Anyways, so we've defined a lot of terms. We have defined SST files, mem tables, write buffer manager, flushing, compaction, indexes, Bloom filters, a lot of information. If you have any questions, please put them in the comments. The next thing I want to talk about, though, is something specific to Kafka Streams. So if you're not a Kafka Streams user, feel free to fall asleep for the next 3 minutes. But this is a cool optimization that Kafka Streams does that reduces the write load to RocksDB and also the read load as well, and reduces the write load to the Kafka Streams changelog topic. So in Kafka Streams, there's this abstraction called a state store, which is basically a combination of a changelog topic, which serves as the write-ahead log, and also a RocksDB instance, which is kind of the index. As you remember earlier, I said that generally in Kafka Streams 3.6 and earlier, the write-ahead log on RocksDB is disabled. That is because there is a Kafka changelog topic on the Kafka cluster, which has a series of, it's a compacted topic that has key values, where the message key header is the key and the value is the bytes actually written into the RocksDB instance. So when I do store.put on the Kafka Stream state store, that goes into the Kafka Stream state store cache, which is an in-memory map of string to value or key to value. And the K and V are generic types actually, but that's kind of an implementation detail. So there's two things that happen here. When the Kafka Streams comes to a commit, then all of these writes are flushed into RocksDB. So that means they go into mem tables, or depending on whether there's a flush or something like that, the writes go into RocksDB, and then they also go into the Kafka changelog topic. In exactly one's processing, there's a couple things that they do to ensure that it's atomic and that you don't get into any weird situations. That's beyond the scope of this presentation because it's about RocksDB. But it's a really, really cool optimization that they do because if, in one Kafka Streams commit interval, you write to the same key 5 times, that means there's only one message to the changelog topic and only one write into RocksDB. Very, very cool optimization. We're playing around with that at LittleHorse right now, actually, to see if we can fool around with our commit intervals to reduce the load, because in workflow engines, there's a lot of repeated writes to the same key, for example, the state of a workflow. So at this point, I wanted to show you guys some code, which is the LittleHorse RocksDB configuration. And that's applicable to any RocksDB user, as also, also I'm gonna, very applicable to any Kafka Streams user. And then we're going to get into some general recommendations. I'll check if there's any comments. Oh, no questions. Good. Okay, so here you can see the LittleHorse RocksDB config setter class. Actually, I should probably show you the server config. So basically, when you are configuring a Kafka Streams application, you create a Java properties object. And you have the option to pass in a class, which is used to set RocksDB configurations. So we do that here. We pass in the rocks config setter class. And this class is responsible for setting all of the configurations of RocksDB. So the first thing that we do is we set a global block cache. So this is something I want to mention about Kafka Streams specifically. The default behavior for Kafka Streams is to create a 50 megabyte cache for every single RocksDB instance, which means that there's no overall limit on the size. And these caches are not shared. They're on a per instance basis, which is why if you have more than 30 or 50 state stores open on a certain Kafka Streams instance, you have really, really high memory usage, for example. And that's not really, really good. You want to avoid that. So what we do here is we set the block cache to a global shared one, which has a configured size, which is passed into the LittleHorse server through LittleHorse server configurations. Optimize filters from memory. This is something that you should generally do. Basically, it's an optimization that tells RocksDB to say, hey, we're using JE-malloc, which is a certain memory allocator. Hang on, I'm getting some message. Okay, yeah, we're using so basically it tells RocksDB, hey, we're using JE-malloc. Why don't you please optimize the Bloom filters to reduce the memory footprint while using that allocator? Next thing is block size. Blocks, so data in RocksDB is stored in blocks. Bigger blocks means you have to have fewer indexes. And one note on block size is that the default for RocksDB and for Kafka Streams is, I think it's like 4 megabytes. However, in production, Facebook, according to the RocksDB documentation, generally uses 16 to 32 megabytes. So we set it to 32 megabytes. The reason why we set it to bigger in LittleHorse rather than 16 megabytes is that bigger means less overall memory usage, and also we have a lot of long keys in LittleHorse, and if you have longer keys, you want to use bigger block sizes. Other interesting things that we do here. Oh, this optimize filters for hits configuration. I will go back to the presentation and show you something on the architecture slide. This is a Bloom filter configuration. So if you recall, Bloom filter is a in-memory data structure that is used to optimize the read path. Basically, Bloom filter, there's one Bloom filter per SSD file, and it will tell you yes or no, does a key exist in the SSD file? And it can have false positives, no false negatives. So because of the way the compaction works, the last level has generally, depending on how you configure it, generally 90% of the data, which means 90% of the SSD files, which means 90% of the Bloom filter memory footprint. There's one optimization you can do where if you know that most of your reads, most of your gets are going to return a value rather than returning null, you can not put a Bloom filter on your last level. If you don't put a Bloom filter on your last level, that saves you a ton of memory, saves you a ton of off-heap memory. at the cost of, if you do a get on a key that doesn't exist, you're guaranteed to load an SST file from the last level into memory to check if it's there or not, because you don't have a Bloom filter on it. Now in LittleHorse, most of our gets, like a very high percentage of them, will result in returning a value, because a lot of these keys are predetermined. Most of our gets will return a value. So in order to reduce the overall memory and allow us to save it for other things, we disabled the Bloom filter on the last level, which saves us a lot of memory overall and allows us to use that memory for things like increasing the overall write buffer manager size and increasing the size of the mem tables. Now, I want to talk about mem table size or write buffer size. That is a configurable option in LittleHorse. We'll get to a recommendation, but generally larger is better. Then the last thing that we do, the last two things that we do, which are notable here in our RocksDB configuration, is we set a global write buffer manager so that there's one thing that configures the maximum size of all of the write buffers in the application. And by default in Kafka Streams, that's not really done. So there's nothing that sits there globally and puts a limit on the data, the memory used by RocksDB write buffers, which means it's a vulnerability to out of memory errors. So this guards against that. And then the last thing we do is we set the max write buffer number to 5. So because by default, Kafka Streams does not have a write buffer manager, which sets the maximum amount of memory that can be used by all of the mem tables, whether they're active or read-only, the Kafka Streams committers decided to reduce the default maximum write buffer per RocksDB instance from 5 to 3. So if you go back to the architecture, you can see here there's 3 write buffers or 3 mem tables in this RocksDB instance. There's 1 active and 2 read-only. That means that if this mem table becomes full, it will force this to flush before I add another one. That hurts write performance a little bit. The default for RocksDB is to have 5 is the max. Kafka Streams uses 3 because that kind of limits overall memory, because now instead of having 5 things in memory, you only have 3. 5 mem tables in memory, you only have 3. So we bumped that config back up to 5, and that's safe to do because we have a write buffer manager, which will force things to flush. And I think that's all I wanted to show you from the LittleHorse code. Now we're going to get into some recommendations, and some of these on this slide are generally universal. So we recommend to use a universal write buffer manager shared across all RocksDB instances on your server. That way you can put a cap onto the off-heap memory reserved for mem tables and reduce the likelihood of out-of-memory errors. Also, you should use SpeeDB because of proactive flushing, very, very useful. You should also have a shared block cache rather than, in Kafka Streams, for example, creating one for each instance. I really, really want to stress that a bigger write buffer size or bigger mem table size is better, because if we go back to this slide, you'll see that when a mem table becomes full, it gets flushed into read-only mem tables, and then read-only mem tables get directly put into SST files in L0. You don't want a lot of SST files in L0 because, number one, that means reads are a lot less performant because they have to check a bunch of SST files in L0. And number two, it means that compactions are a lot more frequent. You really don't want that in RocksDB. Frequent compactions makes you more likely to have write stalls, for example. You want to have bigger SST files. You want to have fewer of them. So can't stress enough how important it is to have larger write buffer size. Also use JEmalloc. I probably didn't pronounce that correctly. Confluent has done a lot of benchmarking, and so did Meta, which says that it's better. I didn't verify any of it, but just use it. Trust me. Also, smaller keys are better. The keys that you put into RocksDB, if they're smaller, it performs better because when you do a lookup, there's some comparator which has to iterate through the key that you're looking for and the key that's in there in RocksDB for to compare it to determine where to look next. Also, if you have bigger keys, you need a bigger block size in order to optimize for lookups as well. Lastly, leave enough memory for the page cache. This is very similar to Kafka, Apache Kafka, but the page cache is highly useful. I think we're going to go like 2 minutes over, but that's okay. And somehow let me fix this slide. Sorry about that. There we go. Better. Okay. Lastly, here's some things you can do to limit memory, which somewhat hurt performance a little bit. So using a larger block size means that you have fewer fewer blocks, which means you also have fewer indexes. You should do that. Like having a larger block size hurts read performance just a tiny bit. You can also optimize bloom filters for hits, which is what I talked about, which is removing the bloom filter on the lowest level. You can optimize bloom filters for memory, which is just a flip that tells RocksDB, hey, I'm using jemalloc. Please optimize bloom filters for jemalloc, and that's pretty close to free in terms of performance, but it reduces memory overall. The last thing you can do is cache your index and filter blocks. That is because if you go back to, I probably should have had more copies of this picture. Anyways, if you go back to here, every SST file has an index on it, and those indexes live in memory. If you have a really big database, like we're talking hundreds of gigabytes or a terabyte, you're going to have a lot of SST files, which means you're going to have a lot of indexes in memory. There is a feature in RocksDB which allows you to put those index files into the block cache, which is an LRU cache, which means if a index block is not used for a certain amount of time, if an index block isn't used recently, then it will get just written to disk and it will no longer be in memory. And that means that the overall memory usage is going to be a lot lower because index blocks can get paged out. However, it's going to hurt your read performance quite a bit because now you're you have to look up the index files from disk, which is a lot slower. But it enables really massive scaling, hurts performance quite a bit, but that's all right. However, I will say though, if you do that, you should pin the L0 index blocks. There's another configuration which says, hey, all the index blocks for L1 and greater, please put them in the cache, which means they can get paged out, but don't ever page out the L0 index blocks. And that's really good for performance. Highly recommend you do that if you go down the route of trying to minimize memory usage. So almost done. Upcoming LittleHorse news I wanted to let you guys know, including updates on upcoming tech talks about other topics and so on and so forth. Going to release 0.7.2, which includes the admin dashboard, followed by 1.0 in a couple weeks, which will be following semantic versioning, means a production-ready stable release with a stable API. Eventually, we're going to have a self-service cloud console, which means you can sign up for LittleHorse Cloud just with a credit card without talking to sales. And entering some POCs with early users, which is what's motivating the 1.0.0 release, because if they're going to be using it, you might as well make the API stable. I think, I'm not committing to this, but I think the next tech talk is going to be how Istio sidecar injection works. It's a little bit more of a niche, but it teaches you a lot about Kubernetes admission control. And it's a topic that I really find interesting. And more importantly, we have a fantastic team member, Edward Kamakaro, who is going to be speaking about a KIP that he implemented at Kafka Summit London. So please, if you're going to London, let me know. We'd love to say hi and also watch that talk. He's fantastic, did a great job on this KIP. It's how you can, it's related to Kafka streams and monitoring your standby tasks. And also, we have some upcoming benchmarks and blog posts about LittleHorse performance, and we'll be sure to mention some of the RocksDB configurations that we set in those blog posts. So I will make these slides public. There's some further reading here. This is the GitHub for the RocksDB configuration setter class. Here's some RocksDB documentation and SpeeDB documentation. Highly recommend you check it out. Lastly, here's how you find us. So I hope this was useful to you guys, and let me know if you have any requests for other topics that you'd love to hear about in future LittleHorse Tech Talks. I think the next one, or pretty soon, we're going to have, I won't be in there. It'll be some of my team members giving talks about stuff that they're passionate about. But really appreciate you guys showing up. Oh, I got some comments here. Caching, filter, and index files has some out-of-memory risk. I should stop sharing my screen, shouldn't I? How do I do that? Hang on. Stop screen. Okay. Caching filter and index files has some out-of-memory risk. SpeedDB has a feature to allow static pinning to enjoy the performance of the out-of-memory risk. Yes, another reason you should use SpeedDB. Digging Bloom filters, paired Bloom filter that reduces the memory footprint by 20%. And that's also great. I didn't want to go into that because I'm definitely not an expert, and I didn't want to say something completely wrong. Thank you for the context. Anyways, we're about 4 minutes over time, which is a lot less over time than most of the LittleHorse daily stand-ups. So I'll take the small win and end it right now. Thanks everyone for joining.